In this video, we are going to talk about how to factor binomials. So we'll be looking at how to factor binomials by using the difference of two squares method and the sum or difference of two cubes method. So first we're going to talk about what it means to be a perfect square or a perfect cube, starting with perfect squares. So we can look at what perfect squares are by squaring whole numbers. So if we square 1 squared, we get 1, 2 squared, we get 4, 3 squared, we have 9. And so forth. 4 squared is 16, 5 squared is 25, 6 squared is 36, and so forth. So it is a good idea to kind of have these perfect squares committed to memory, just because it makes it that much quicker. Oh, I'm talking and making mistakes here. 9 squared is not 100, 9 squared is 81, 10 squared is 100. So it's a good idea to have these kind of committed to memory so that you can easily recognize perfect squares and therefore factoring. So I would recommend even having them memorized up to 15 squared would be helpful. But let's look at what it means for a variable expression to be a perfect square. So I'm squaring x to the first by using the product rule, not product rule, the power rule, by multiplying the exponents. That gives me x squared. X squared squared is x to the fourth. X cubed squared is x to the sixth. X to the fourth squared is x to the eighth. Again, I'm getting this by multiplying the exponents together. And I see that the resulting perfect squares all have even exponents. So the next perfect square would be x to the 10th or x to the 12th, and the variable x is just a placeholder, so it could be any variable. So if you have an even exponent on a variable, that means that you have a perfect square. All right, and it's also important to note to go backwards. So if you have x to the 8th and you want to find the square root, that would be x to the 4th power. If you have x to the 4th and you want to find the square root, it would be x to the 2nd power. You can just divide the exponent by 2 to take the square root. All right, let's take a look at perfect cubes. So we could cube whole numbers. 1 cubed is 1, 2 cubed is 8, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, and so forth. So these you should have committed to memory as well. If you know up to 6 cubed, you should be okay. It really doesn't take that much to kind of check in your calculator 7 cubed or so forth. But let's take a look again at variables. X to the first cubed would be x to the third. If we have x squared and then we cube that expression, we have x to the sixth. Again, multiply the exponents. X to the third cubed is x to the ninth. X to the fourth cubed is x to the 12th, and then that pattern would continue. So here the exponents on the variable are multiples of 3. The next one would be x to the 15th. So if you have a variable expression where the exponent is a multiple of 3, like 3, 6, 9, 12, 15, 18, 21, so forth, you know that that is a perfect cube. And you could take the cube root, go backwards by dividing the exponent by 3. So the cube root of x to the 9th would be x to the 3rd. The cube root of x to the 12th would be x to the 4th, and so forth. Okay, so we're going to see how looking at perfect squares and perfect cubes can help us to factor binomials. We're starting with the difference of two squares. So this is a method that will work for certain kinds of binomials. These binomials have two terms that have a difference between, so a minus sign in between, and each of the two terms is a perfect square, which means the coefficient is a perfect square, and all of the variables in that term have even exponents. Now, when we were multiplying, you might have seen that when we multiplied the sum and the difference of two terms, we actually got this structure. So to factor, which means to kind of reverse that process of multiplication, we're just going to take the square root of each of the terms and write them in what we call conjugate pairs. So one of them has a difference, and one of the binomials has a plus sign. So we're writing it as the sum and the difference of those two square roots. All right, so let's take a look at these examples here. We have 4 examples where we'll use this method of factoring. Right, so the first example we have x squared minus 81. Again, it's important to note that you do have perfect squares here. So we have two terms. There's a difference between them. X squared is a perfect square. 81 is a perfect square. So we can go ahead and set up our two binomials and take the square root of each term. Square root of x squared is x, that goes in the first position. Square root of 81 is 9, that goes in the second position. One binomial has a plus sign, the other has a minus sign. It doesn't matter which one it is. In this second example, we have a GCF first, so we should certainly take that GCF out. That GCF is 5, and when we do that, we have the binomial a squared minus 25, and the a squared minus 25 is the difference of two perfect squares. So we set up our two binomials, take the square root of a squared, which is a, take the square root of 25, which is 5. One set gets a plus sign, one gets a minus sign. In the third example, we also have a GCF. 36 and 64 are both divisible by 4. So we are going to divide each term by 4. Oh, and there's a z in common as well, so I'll take that z out. Without taking out that z, we couldn't use the method of a difference of two squares because z to the first is not a perfect square. But when I do divide by 4z, I'm left with 9x squared minus 16y squared, which is the difference of two squares. The square root of 9 is 3, and so I have 3x and 3x in each of the first positions. And the square root of 16 is 4, and we have y squared. So we have plus 4y and minus 4y. Notice again that I have that GCF term there as well. In the last case, I do see that I have x to the fourth, but if the exponent is even, it is a perfect square. So I could take the square root by dividing the exponent by 2. So I have x squared and x squared. The square root of 1 is 1. So I have 1 and 1. Here, one set has a plus sign, the other set has a minus sign. Now, this binomial here, x squared minus 1, is also the difference of two squares because x squared is a perfect square, 1 is a perfect square, you have a minus sign in between. This first binomial is not a perfect square, a difference of two squares, because it's not a difference. So we are going to continue to factor just that second binomial. The first one will stay the same. X squared plus 1. And then we have to factor a difference of two squares again. X at x plus 1 and minus 1. Okay, so let's go on to the next and last factoring method we're going to look at, which is the sum or difference of cubes. And in your text, you have the description of these formulas, so you can read about where these formulas come from, or just verify that the formulas work by multiplying together. But we need to first recognize that we do have a sum or difference of two cubes. So we have, in this case, we can have a sum as well as a difference. Each term has to be a perfect cube. So the coefficient has to be a perfect cube, and the variables have to have exponents that are multiples of 3. So the formulas are given here, and in your book, once again, take a look at them. What we're going to do first is build a binomial where we take the cube root of each term, and then build a trinomial where we start to look at perfect square or multiplying squares and two terms together. So let's take a look at the examples. Oops, let me go back here. Okay, in this first example, we have z to the third plus 64. Again, notice that both of these are perfect cubes. We have the sum of two cubes, so we're following the formula that you see up top, which means we're starting with a binomial. That binomial will have the same sign as our original binomial. And we're going to take the cube root of each term. So the cube root of z to the third is z. You could just divide the exponent by 3. The cube root of 64 is 4. So my binomial is z plus 4. All right, so I'm going to use my binomial to build the trinomial. So the first term of the trinomial will be squaring the first term of the binomial, which is z squared. Then I'm taking the opposite sign, so negative, multiplying the two terms together, 4z, and then squaring the last term, 4 squared is 16. So my signs are always the same, as the original polynomial, the opposite for the second term, and then always positive. In the second example, we have 216 minus n to the third. Once again, I'm going to set up my binomial times a trinomial. Find the binomial first and use those terms to get the trinomial. So I'm taking the cube root of 216, which is 6, minus, same sign, cube root of n to the third is n. Now I'm going to square 6, which is 36, opposite sign plus, multiply 6n, and then square the last term, n squared. The order of the terms is important, so make sure you have the order in the same appropriate order as your original polynomial. All right, the third example, I do have a GCF of 2, so I'm going to take that out first. Otherwise, I really can't do anything because 16 and 54 are not perfect cubes. But luckily, when I do divide by 2, I do get coefficients that are perfect cubes, 8 and 27. The GCF of 2 is going to come down. And now I'm building my binomial. Cube root of 8 is 2. Cube root of m to the third is m. Cube root of 27 is 3. Cube root of n to the third is n. Now when I'm building my trinomial, let me pause this, I am squaring the entire first term. 2 squared is 4. M squared is m. Now I'm going to take the opposite sign. So I have a plus sign here. I'll have a minus sign. And then I'm multiplying these two terms together. 2 times 3 is 6. M times n is mn. So that term is negative 6mn. Then I'll take the last term and square it. 3 squared is 9. And n squared. That last term is always positive. Right, finally, the last example, we have another sum of two cubes. Again, I know these are cubes because the exponents are multiples of 3. So when I find the cube root, I'm just going to divide the exponent by 3. So the cube root of x to the 9th is x to the 3rd, and the cube root of n to the 12th is n to the 4th. Now I use those terms to get my trinomial. Squaring x to the 3rd, which means I'm multiplying the exponent by 2. That gives me x to the 6th power. Take the opposite sign, minus, multiply the terms together, x to the 3rd, n to the 4th. Take the last term, square it, n to the 4th squared is n to the 8th. Again, it's a square term. Make the exponent, multiply the exponent by 2. All right, so I hope you enjoyed this video. Let me just end by giving you a overview of the methods, because many times you'll have more than one method that you need to employ to multiply polynomial, or not multiply, excuse me, factor polynomials, which is the reverse of multiplication. So this is really your general strategy that you should follow. If you have a binomial, you can check to see if it's a difference of two squares. If it's a sum of squares, you can't factor it, but if it's a sum or difference of cubes, you can factor it using those kind of formulas. If you have a trinomial, you have that kind of regular method where you can go right to your binomials, or you can use that grouping method, which is also called the AC method. There are some special formulas that you'll see in the textbook for perfect squares, and you can follow those formulas as well, but if you just know that regular method and that grouping method, you'll be fine. And then if it's 4 terms, grouping is the only way that you have to go. But of course, the very first thing you should always try and do, and that's the first thing that you see here, is look for a GCF. So always try to get the GCF first, then just remember to check all of your factors along the way. And you could always check your factorization by multiplying everything back together. If it doesn't give you back the original polynomial, something is wrong. Go back and check.